Hello and welcome. This is going to be our lecture video for February 5th. Let's go ahead and get started with a quick do now. How much should you invest in an account that pays 6% annual interest compounded continuously if you want exactly $8,000 after 4 years? All right, so once we see that word continuously, we should immediately key into the formula A equals PE to the RT, and then fill in the values that you have. The one kind of difference here is that because I would know my ending balance, I'm going to be filling that in to A and leaving P as a variable. So 8,000 equals P times E. The rate is always a decimal, and time was 4 years, so times 4. All right, now we need to solve for P. This doesn't require any sort of fancy math like a square root or a logarithm. Because E is just a number, this part can be computed. We can plug this into our calculator and we get about 1.27. But keep all those significant digits in your calculator so that you can just do 8,000 divided by second answer, and it will carry down all of those significant digits and give you a more precise answer. So our principal should be $6,293.03. You might be wondering, why did I round up instead of down for the penny there? Well, we always round up. Always round up. If you round down, even though you're rounding down only 2 tenths of a cent, that could be enough that by the end of this, you end up, a penny or two short of that $8,000. So just always round up, and then you'll probably get nearly exactly 8,000. You might get 8,000 and a penny or something like that, but I'll guarantee you get the full amount that you want. Goal for today is to understand the notation of logarithms and continue to work with their properties. Why are we doing this? So we can use logarithms to solve for variables in the exponent. Can we solve equations where the variable is in the exponent without a logarithm? It is possible in very specific equations where we can write both sides with the same base. So look at the side with the variable, then look at the other side and say, can I rewrite this side as an exponent with an 8 in the base? And this one is set up in a way that we can do that. We can rewrite that 64 as an 8 squared. So rewrite with the same base. All right, at that point, we can now cross out those 8s, a step I call dropping the base. All right, and what we're essentially saying here is for these two sides to be equivalent, their exponents have to be equivalent. So 3x plus 1 equals 2. If these match, then these will match, and the equation will be true. And now we just got a nice easy equation to solve. 3x equals 1, divide by 3, divide by 3. X equals 1/3. All right, let's try another one like that. 625v equals 25 to the 1 minus 3v. Well, here we got variables on both sides, but if you know your powers pretty well, you might recognize 65 and 25 share a common base. So 625 is 5 to the power of 4. All right, so I can rewrite this as a 5 to the power of 4 to the power of v. And the 25, hopefully we all know that that's 5 squared. All right, copy down the rest of it. And now, a property of exponents is when I have a stack of exponents, I can just multiply that. So I'm going to distribute this 2 over here and rewrite this as 5 to the 4v equals 5 to the 2 minus 6v. And at this point, we can drop the base. 4v equals 2 minus 6v, add 6v to both sides. We get 10v equals 2. Divide both sides by 10. and v will equal 1/5. All right. One more. Why don't you try this one on your own? I'll embed a question here for you to answer it. All right, so I'm going to do this one real quick. So this could be a 3 squared to the 3x. This could be rewritten as a 3 cubed to the 4x plus 1. This distribute on the top, we get 6x equals 3 to the 12x plus 3. Drop the base. I forgot my x. 6x equals 12x plus 3. I'll subtract 12x from both sides. Get a negative 6x equals 3. Divide both sides by negative 6. X equals negative 1/2. And then these are pretty easy to double check. You just plug that number back in, see what you get. So 9 to the power of negative 3/2 is 0.037. And then 27 to the power of negative 2 plus 1 would just be negative 1 is, again, 0.037. So it does check out. All right. Let's just go over all things logarithms one more time, so we just have it in our notes really well. If I have an equation, a to the b equals c, this is our power, this is our base, this is a constant on the other side. This can be rearranged to be log base a of c equals b. So notice where everything moved to. A is still called the base, and that helps us do this rearrangement, that they're both the base, they're like the low number. These two numbers switch places, and this is now called the argument. And we say log base a of c is equal to b. But you say base, and then you say whatever that number is down there, and then you say of c. So it's sort of like function notation, and that it has that word of in there. Now, a few kind of things to keep in mind is if I just have log of 8, if I don't write a base, it's assumed to be 10. And we do a lot of stuff in log base 10 because it's really helpful with scientific notation, which is always has 10 raised to some exponent, so 10 is always the base. So that's why it's probably our most common logarithm to use is log base 10, and that's why you press the log button on your calculator, the one on the left side there, it assumes to be base 10, and then there's a way to change it with math, and we'll talk about that in just a second. Let's see. So what is the log of 1? Well, we can just plug that in and investigate it, and we get log of 1 is 0. And this actually works for any base. So it works with base 10 because 10 to the 0th equals 1, but really anything down here raised to the power of 0 equals 1. So it can be any number. Can be any base, and this will still work. Well, what would happen if I tried to take the logarithm of 0? So now I'm saying 10 to what number equals 0? Well, I can't raise 10 to a negative number big enough that it goes all the way to 0. Let's just try this in our calculator, see what it says. Log of 0 says air domain. This is undefined. And it's for the same reason Alice can never shrink all the way to a height of 0. You cannot, even with a base of 0.5, you can't raise that to a high enough power to shrink it to 0. Let's see other properties. Let's talk about ln, this is log base e. Another very common base for logarithms is e, so it gets its own special notation. You know, especially because, with compound interest, e is always the base in that exponent. Let me think if there's anything else I want to say about logarithms in general here. I think we're good to move on. So how do I plug the following into my calculator? Log base 2 of 16. So you might see that we have a slight problem that if we just press log, it always assumes base 10. Well, in some of the newer calculators, there is a way to manually input the base. You can press this math button. Scroll up is the quickest way to get there, to log capital base. And now that lets us put in a 2 of 16. Do you know what it's going to say when I press enter? 4, because 2 to the 4th equals 16. What if we don't have that special feature? Well, we can do the same thing, but you have to do the change of base formula. So you do log of the argument divided by log of the base, and that accomplishes the same thing. And actually, this is sometimes a little bit quicker than going into that math menu. So I often just do my logarithms this way to save myself having to scroll through that menu and then plug the numbers in. And you get the same answer, as we can see there. Okay, now properties of logs. These are based off of our properties of exponents. If you take our properties of exponents and rearrange them into logs, this is what you would get. I'll encourage you to just pause this and make sure you got these all copied down. These inequalities down here, kind of important. It says, we can't take the log of a negative. I guess let's write that down explicitly. We can't take the log of 0 or a negative, right? So again, if you think back to Alice, her height can never go to 0. Her height also never becomes negative through a finite number of steps. So yeah, can't take the log of 0 or a negative, and the base b here can't be 1. Yeah, and that should also make sense because 1 raised to any power is still just 1. So you can never, if you want to do log base 1 of 2, you can never get 1 to be a 2 by just raising it to an exponent. So 1 to any power is still 1. All right. Change of base formula. Get that one copied down. Pause it here. All right, so if you're ever told to expand, what that means is use the properties of logarithms to write this out with as many logarithms as you can and absolutely 0 operations inside the arguments. So no operations in the argument. So here I've got lots of operations. I have exponents, I've got multiplication. So what I'm going to first do is rewrite this as log of a squared plus log of b cubed, because multiplication inside the argument can become addition outside of the logarithm. And then those exponents can jump in front. Exponents inside the argument can become coefficients. So 2 times the log of a plus 3 times the log of b, and now there's no operations left in those arguments. All right, this next one would be log of a minus log of the square root of c, because division can become subtraction, and then that square root could be rewritten as a to the power of 1/2 and then brought out in front. So this could be log a minus 1/2 log c. All right, In this one, we got to bring that 1/2 out in front at the beginning. So 1/2 log of c over b, which then will turn into subtraction. So log c minus 1/2 log b. The 1/2 will get distributed there as well. All right, this one here, go ahead, try it on your own. I'll embed a question here for you to put your answer. All right, you should have gotten something like 3 log a minus log b minus 2 log c. All right, we would subtract both of these and then we could distribute the negative. And there we go. All right, condense means go in the exact opposite direction. And some fun stuff can happen when you condense because like with this first problem, we'll see this log base 4 of 32 and log base 4 of 2, neither of these are exact integers, but when we put it together, this would become log base 2 of 32 over 2, but then we can simplify that. We can now write this as log base 2 of 16, and then 2 to what number equals 16? 2 to the 4th equals 16. So now it does become just an integer. All right, and we'll do this next one. We've got addition, so that'll turn into multiplication. The 6 will become an exponent. We get log base 2 of x to the 6th, y to the 5th. And 5 also becomes an exponent. And when you have a large argument, it's often worthwhile to put it inside of a set of parentheses so we don't think that we're taking the log of just the first part and then multiplying by the second part. All right, 2 more. Why don't you just pause and try them on your own separate piece of paper, but I won't embed a question for these ones. This becomes log of 4 plus log of x minus log of y. And this one here becomes 4 log base 9 of x minus log base 9 of 729. Except for log base 9 of 729, I'm pretty sure that that is an exact value. So plug it into my calculator. I use the change of base formula to do it more quickly, and that becomes a 3. So 4 log base 9 of x minus 3. All right, so Alice was walking through Wonderland and came across a new cake. This was base 10 cake. That means that for every ounce you eat, you grow 10 times your previous height. Alice is currently 1 foot tall because she drank some of that shrinking beverage and just enough to make her 1 foot tall. But now she wants to be exactly 5 feet tall. So can she be at her normal height again? How much should she eat? So let's set this one up. We'll use her final height y equals ab to the x, where a is her current height and b is the strength of the cake. Also, x is the amount of cake, and y is final height. All right, let's plug in the values from the problem, and we get her final height wants to be 5. Her current height is 1. The strength of the cake is a 10, and the amount is undetermined as of yet. So, how do we do this? Well, we can ignore that 1, because 1 times anything doesn't change it. We know our variable is stuck in the exponent, so we throw a log at it to knock it out. And so we rewrite the word log. Base of the exponent becomes the base of the log. 5 comes over here, and x goes over here. And then you can double check with the swoop. 10 to the x equals 5, and make sure you get back to your original equation. We do. And then this can be plugged into our calculator. Because it's log base 10, we can just do log of 5 equals x. And that's just 2 keystrokes, log 5. There's 3 to include the enter, and you get x equals 0.7. We round up just a little bit. Let it maybe be just a hair taller than 5 feet. And let's give it a unit. 0.7 ounces. All right. Do I have another problem here? No. I'll embed a few more for you to try, but that's the end of this lecture video. Have a great rest of your day.